Next, I'd like to talk about the characteristic root technique, which when I first learned about, I thought was so cool. So let's talk through this. So given a recurrence relation, a sub n plus alpha, which is just a constant, times a sub n minus 1 plus b sub b times a sub n minus 2 equals 0, gives us a characteristic polynomial of x squared plus alpha x plus beta equals 0. If I find two roots of this characteristic polynomial, remember roots where would be the solutions to this characteristic polynomial, then the solution to the recurrence relation is a sub n equals the first root to the nth power plus b times the second root to the nth power. And a and b are constants determined by the initial conditions. Now, what does that mean? I think we're going to do a bunch of examples. What do you say? So let's take a look at this first example. I have a sub n equals 7 a sub n minus 1 minus 10 a sub n minus 2 with my two initial conditions. So we need to rewrite this relation so it's in the correct form. So now I have a sub n equals, I need to get one of the sides equal to 0. So I have a sub n minus 7 a sub n minus 1 plus 10 times a sub n minus 2 equals 0. Now I have the polynomial x squared minus 7x plus 10. Next I need to factor. So I'm wondering what are some factors of 10 that add up to negative 7. That's going to give me a negative 2 and a negative 5. If you don't remember to factor, there's lots of factoring resources on the internet, but I'm sure you do because you're in discrete structures, so you passed college algebra. Awesome. So we've gone ahead and factored this. Now, in order to find the roots, I need to set each of these factors equal to 0. So I have x equals 2 and x equals 5 are our roots. I plug these roots into the equation a sub n equals a times r1 to the n plus b times r2 to the n. So let's clear this, knowing that my roots are at 2 and 5, and make sure we have a little bit more room. Erase. So I am substituting my roots into this equation. And I'm going to use this equation to solve for a and b. So now I have a sub n is a times 2 to the n plus b times 5 to the n. Now I said in my last, in the couple slides ago, that these terms a and b were determined based on our initial conditions. So we're going to go ahead and solve for a and b, and we need to do that by plugging in n equals 0 and n equals 1. This is going to give us two equations with two unknowns so we can solve this systems of equations. So for a sub 0, that's 2. I have a times 2 to the 0 plus b times 5 to the 0. Well, 2 to the 0 is 1, right? And 5 to the 0 is 1. So I have 2 equals a plus b. That's my first equation. Next, I'm going to plug in n equals 1. So I have a sub 1 is 3, which is a to the 2 to the first plus b times 5 to the first. So I get 3 equals 2a plus 5b. Here I have my system of two, oops, I circled the wrong one. Here I have my system of two equations. And we can solve these any way you'd like to solve a systems equation. You could solve them by substitution, you could solve them by elimination. I'm going to go ahead and solve this system of these two, here's my system, by substitution. So I have 2 equals a plus b. I want to solve this for a single variable. How about b? So I subtract a from both sides. So I have 2 minus a equals b. I'm now going to substitute this into my second equation. 3 equals 2 times a plus 5b. But I now know what b is equal to. So I have 3 equals 2a plus 5 times 2 minus a. 3 equals 2a plus 10 minus 5a. I'm going to go ahead and subtract 10 from both sides. Negative 7 equals 2a minus 5a, which is negative 3a. I divide both sides by negative 3. 7/3 equals a. Awesome. Now I need to solve for b. I can plug that back into either of my equations and solve. So I'm going to go ahead and plug this into my original equation. 2 equals a plus b. That means 2 equals 7/3 plus b. Well, 7/3 is 1/3 more than 2, so I get negative 1/3 equals b. Now I have my coefficients a and b, right? So I can rewrite this. Final answer is a sub n equals a, which is 7/3, times 2 to the n, minus 1/3, which is b, times 5 to the n. So here we have it. We have solved this reoccurrence relation using the characteristic root. I think we should try one more. How about that example from the beginning of this section that we couldn't solve using our previous methods? So I'm going to go ahead and rewrite this initial equation in the correct form. So I have a sub n minus 5a sub a to the n minus 1 minus 6a to the n minus 2 equals 0. That leaves me with the characteristic equation x squared minus 5x plus 6 equals 0. I'm going to go ahead and factor this. That means I have the roots x equals 3 and x equals 2. So I can rewrite my roots into my equation. A sub n equals a 2 to the n plus b 3 to the n. And I want to go ahead and make sure I write these in this equation in this form, but now I need to plug in n equals 0 and n equals 1 in order to find a system of two equations. So if n equals 0, I have 2 equals a 2 to the 0 plus b 3 to the 0, so 2 equals a plus b. That's kind of familiar to what we had before. Next I have a sub 1 is 5, which is a 2 to the 1 plus b 3 to the 1, so 5 equals 2a plus 3b. I'm sure you can already see the answer here, but let's go ahead and solve this anyways. I'm going to go ahead and solve my system of equations. If I have 2 equals a plus b, that means 2 minus a equals b. I'm going to substitute that into my second equation because, again, these two denote our system of equations. And what am I going to do? That gives me 5 equals 2a plus 3 times 2 minus a. I'm just substituting for b. So 5 equals 2a plus 6 minus 3a. That means 5 equals negative a plus 6. If I subtract 6 from both sides, I get negative 1 equals negative a. So this means a equals 1. And if I have 2 equals a plus b and a equals 1, that means 1 equals b. So my equation, final answer, is a sub n equals 2 to the n plus 3 to the n. The last thing I want to talk about is the characteristic root technique for repeated roots. This could be the case if our polynomial factors to x minus 3 times x minus 3. Right here we'd only have one root to speak of, which would be x equals 3. It just has a multiplicity of 2. It occurs twice. So if I'm given a recurrence relation and a characteristic polynomial, and I only have one root, then the solution of the recurrence equation has changed to this. Notice we threw in a factor of n. That's the only thing that's different. And a and b are still constants we have to solve for that are determined by the initial conditions. So let's work out an example. I have a sub n equals 6, a sub n minus 1, minus 9, a sub n minus 2. So I'm going to get this in the correct form. A sub n minus 6, a to the n minus 1, plus 9, a to the n minus 2 equals 0. The factors that add up to 9, the factors of 9 that add up to negative 6 are negative 3 and negative 3. So let me first actually write my characteristic polynomial, and then we factor this to x minus 3 squared. So I have x minus 3 equals 0, x equals 3. So let's re-put this in our new equation. I have a sub n is a to the 3n plus b times n 3 to the n. And I'm going to plug in a sub 0. So I'm going to plug in n equals 0 and n equals 1, just like before, to get a system of two equations that I can solve. So for a sub 0 is 1, that means a to the times 3 to the 0 plus b times 0, because that's my n, times 3 to the n. This term is just going to cancel out entirely, so I'm left with 1 equals a. Oh, that was convenient. Let's go ahead and solve for a sub 1. A sub 1 is a 3 to the first times b times 1 times 3 to the first. So a sub 1, which was 4, it's important to remember that it was 4, is 3a plus 3b. So now I need to substitute in a equals 1, right? Because I already figured that out. So I have 4 equals 3 times 1 plus 3b. I subtract 3 from both sides. 1 equals 3b. So I have 1/3 equals b. So my new equation, final answer, a sub n equals 3 to the n plus 1/3, that's my b, times n times 3 to the